Hello everyone, this is the lecture number 4 in this course, Advanced Aircraft Control System. In today's lecture, we will be taking an example through which we will solve an equation which is defined in the state space form. And also we'll have the MATLAB code how we can find the solution of the states of that system. And also we'll have some concept on asymptotic stability, how the system is going to behave over time. This is very important concept in modern control or classical control techniques. After having all this stuff, we'll conclude the lecture. So let's start the lecture. First, let's define the problem. We have the problem. So we'll take a simple OD and also we'll discuss how the OD can be converted into state space form. So we have the second order system, x double dot plus 3x dot plus 2x equal to u. And initial condition given to us x not equal to 0 and x dot not equal to 2 or 1. You can assume this is the position and this is the velocity of the state. So now here, one more thing here. This is the, maybe you can assume this is the control, or maybe you can assume this is some external term, which is not the part of the natural dynamics of the system. So the question is, one more thing also given to us, the output equation. This is a state equation, we can assume. The output equation given to us, output equation is y equal to 3x plus 3. 2x plus 2x plus x dot. Let's assume this is the output equation. First question is, study the system in state space, and second, find the status matrix which will transform from initial state to some other final state. And third question is, find the response of the system if u is unit step function. So this is the problem to us. Now we will be working on this problem, how we can find the state space model, and also how we can find the solution of this system solution. So here, the system is given to us x double dot plus 3x dot plus 2x equal to 2u. So if you notice in this equation, this is not in state space form. As you know, the state space, if you're writing the system in state space form, we have to come up the first order ODE. So we need to convert the system first order ODEs. Okay. So for that, we need to apply the change of variables. So let's assume x1 equal to x and x dot equal to x1 dot. Let's denote this is as x2. So from these two condition, we can write x2 dot equal to, we can write from the equation given system, we can write x double dot equal to minus 3x2 minus 2x1 plus 2u. So we are having two systems. One is x1 dot equal to x2 and x2 dot equal to minus 3x2 2x1 plus 2u. So this is basically as first order ODEs. So from these two equations, we can write the state space form x1 dot, x2 dot. These are the derivative of the state vector, and the matrix A matrix 0, 1, -2, and -3. And here we have the state vector x1, x2 plus the control matrix 0, 2, and u. So this is basically, I can write x dot, this is A, this is x, this is b, this is u. So here we can simply write x dot equal to ax plus bu. So this is the state space form of the given system. Now, also we are given the output equation. So this is the state equation. You can write, and the output equation given to us, y equal to 3x plus x dot. So x we have denoted as x1. This is the x1, and x dot given to us is x2. So we can write 3x1 plus x2, or we can write 3, 1, x1, x2. So this is the complete state space model given to us. Now, to find the solution of this system, first and foremost step is we have to find the state transition matrix for this particular example. So let's find that state transition matrix. This is already we have found E8 e to the T equal to inverse Laplace transform of Si minus A inverse. So this is the state transition matrix already we had in the last lecture. So from this, if you substitute all the terms, we can write the matrix. So this is S is the Laplace term. I is that into matrix. We can write S0, 0, S. And A already we have 0, 1, -2, -3. And this is our inverse of it. So from this we can write S -1, 2, S plus 3 is the inverse. Now, from this further, we can simplify this expression. We can write S squared plus 3s plus, this is S, plus 2, and the matrix S plus 3, 1, -2, and S. This is we can write. Now we have to simplify this matrix. So we have to work on the individual terms of this matrix. So now using partial fraction, we can go step by step. So let's work on the first term of this matrix. Let me define this equation number 1. So first term is S plus 3 divided by S squared plus 3S plus 2. So we can apply the partial fraction. We can write this expression as A upon S plus 1, and we can write, okay, also this term also we can simplify further as S plus 1 and S plus 2. So you can simplify this term. So this we can write further. can write 1 upon s plus 1, s plus 2, s plus 3. This is s plus 3. So from this we can write a by s plus 1 plus b by s plus 2. And from this we can write s plus 3 equal to a s plus 2 plus b s plus 1. So we'll find the a and b of the from this equation. So when a is equal to minus 2, so we'll have b term. So b will get minus 1. And when a is equal to minus 1, we'll get a term a equal to 2. So from this we can write s plus 3 divided by s plus 1, s plus 2 as 2 upon s plus 1 minus 1 by s plus 2. So you can write. And similarly, the same way we can find the rest of term. 1 by s plus 1, s plus 2, we can get, I'm not going to the full step, so we can try s plus 1 minus s plus 2 and minus 2 upon s plus 1, s plus 2, we can get minus 2, s plus 1 and plus 2, we can write s plus 2. And s upon s plus 1, s plus 2, we can write minus 1, s plus 1 plus 2 by s plus 2. So now we have found all the terms of equation 1, the terms inside the matrix. So now we can write from equation 1, we can write Laplace transform e to the power at, which is nothing but this expression, this whole thing, this expression. So now we can write, we can substitute all the terms inside. So first term will be 2 by s plus 1 minus 1 by s plus 2 and 1 by s plus 1 minus 1 s plus 2 and minus 2 s plus 1 plus 2 s plus 2 minus 1 s plus 1 plus 2 upon s plus 2. This is the matrix. Now, if you take the inverse Laplace transform for this equation, we can write taking inverse Laplace transform, we get e to the power at equal to, if we apply the inverse Laplace transform, we can write 2e to the power minus t minus e to the power minus 2t, the second term of this. This is we can write, and this is can go to e to the minus t. So now for the second term, we can write e to the minus t minus e to the minus 2t, and this is 2 minus 2 e to the minus t minus e to the minus 2t, and e to the minus t plus e to the minus 2t. So this is the matrix in time domain. Now we'll find the complete response of the system. So here we have to use So here we can use the find from the solution of state equation. We know that x of t equal to e to the power at x naught. This is already have found in the last lecture. 0 to t e to the power a t minus tau b u tau d tau. This is the expression we had, right? So here, one thing, basically here, our u of tau is the unit step function. Unit step function. This is already given in the problem. So now, we can write, further we can write from this. So e to the at already you have. So if you multiply e to the at into x naught is given to us. So in our case, x naught is, we can write 0. So if I write in capital, so here we can write x naught is 0, 1, right? So here, because this is x1, t equal to 0, x2, t equal to 0. So this is how we can write. So in this, that's why initial value of x1 is 0 and initial value of x2 is 1. So we can find the, so if you multiply with 0, 1 to this e to the at matrix, we'll get e to the power minus t minus the minus 2t and minus the minus t plus e to the power minus plus 2 into e to the minus 2t. And for the integral term, we can write 2 0 to t e to the minus t minus tau minus e to the minus 2 into t minus tau, and this is also you can write, we can take common 2, so here so we can put big bracket and dt. Okay, and the second term 2 0 to t big bracket 2 e to the minus 2 t minus tau minus e to the minus t tau d tau and d tau. So this is the another vector. Now we have to simplify all these terms. We will simplify both the terms. So since also we have a given B matrix given to us 0, 2, and already we are having x1 0, x2 0 is 0, 1 given to us. So now we'll try to find the first term in the second vector. This term first we'll find, this term we'll first find, then we'll find the second term. So let's start. The first term we can write 2 0 to t e to the minus t minus tau minus e to the minus 2 t minus tau d tau equal to 2 e to the minus t 0 to t, if they were tau, because t is here, we can assume constant here. Here the only integral term tau, and d tau minus 2 e to the minus 2t 0 to t e to the 2 tau d tau. And from this, we can further write 2 e to the minus t, e to the minus e to the tau 0 t minus 2 into e to the minus 2 tau 2t. And this is e to the power 2 tau 2 and 0 t. So if you further simplify, we'll get 2 e to the minus t, e to the minus e to the t minus 1, e to the 0 is 1, and 2 e to the minus 2t, e to the 2t by 2 half. And from this further we can write 2 e to the 2 e to the minus t 1 plus e to the minus 2t, or we can write 1 minus 2 e to the minus t plus e to the minus 2t. So this is a solution of the first term in this vector. This is the solution of this. Now we'll work on the second term. Similarly, we can write 2 for the second term, t 2 e to the minus 2, 2 t minus tau minus e to the minus t minus tau d tau. And from this, we can easily find the same way you can proceed. So the final value is 2 e to the minus t and 2 e to the minus 2t. This is the final expression. And if you write everything, if you substitute all the terms in our solution expression, in this expression, so we can write the solution for xt. We can write x of is the vector. We can write x1 of t, x2 of t equal to e to the minus t minus e to the minus 2t minus e to the minus t plus 2 into e to the minus 2t. And plus, we found the expression here. We can substitute 1 minus 2 into e to the minus t plus e to the minus 2t. And 2 e to the minus t minus 2 into e to the minus 2t. So this is the vectors. And if you further simplify, we get 1 e to the minus t and e to the minus t. So this is the solution of the state equation, x dot equal to x plus bu. And the output equation we can write, already have the output equation. So y, this is the state equation, solution of state equations. And the output equation y equal to cx. So here, c is basically 3, 1 already given to us, and x1 of t, x2 of t. Now, x1 of t is basically here, x1 of t is, this is x1, small x1. This is 1 minus t, and x2 t you can write e to the minus t. So if you substitute these terms in this expression, we get, we can write 3 minus 2 e to the minus t. This is 1. So this is our output equation of the system. Now we'll go to the MATLAB code. So MATLAB code here. So this is the MATLAB code. So here, so Professor Singh helped me a lot for preparing the MATLAB code for this course. He's also instructor of this course. So he'll be covering the six-term model and also some control algorithms for this course. So now we are having the solution. Here we are having this is our solution, right? This is our solution, and we have two state equation, x1 of t and x2. So we'll plot these expressions here. So we are simulating this code for 0 to 10 second. And here, if you notice, this is our 0 to 10 second, and this is the expression for x1 t. This is the expression for x2 t. And if you notice here, this code can be useful for you. You can write the code and can test and verify in your MATLAB window. So here, if you notice here, x1 of t goes to 1, right? This goes to 1. Why? Because e to the minus t tends to infinity, e to the minus t goes to 1. This is e to the minus t goes to 0, because if the t is going to be infinity, so it will be 0. So x1 of t goes to 1, and this goes to 0 as t tends to infinity. So here, this is what the same thing we can see from this figure. So here, the important concept is asymptotic stability. So here we can say that x1, this is the plot for x1, this is the plot for x2, right? But x1 is t, instead of going 1, it is going, sorry, instead of going to 0, it is going to 1. But x2 is going to 0. So x1 of t is not asymptotically stable. But what is the definition of the asymptotically stable? If the system state goes to 0 as time tends to infinity, doesn't matter where it is starting. But in the x1 of t, it is goes to non-zero value, 1. So now I'll define what is asymptotically stable. Let me write asym. So let's assume we have two regions. Let's assume we have two regions here. And for example, this is some parameter x, it's just t. And let's say we have having two regions. One region, let me define, this is the delta, minus delta. Then another region, let's assume. In the control system book, it is well explained. So there is another region, r epsilon minus epsilon. So we can assume there are two circles. One is the smaller circle, another is the bigger circle. So, and let's assume, sorry, instead of t, I can say this is the time axis and this is the x of t. So does not matter where it is starting. If it is starting in some point, for example, here, some point here, and over time, if it can go anyway, but over time, if it goes to 0, we can say if it is like, it can go like this and go like this. It should go to 0. It should go to 0. So it means I can say if x of t naught is starting somewhere between less than delta or less than epsilon, let's assume that some value c maybe, and if limit t tends to infinity, x of t is close to 0, then we asymptotically stable. This is how can define. So in this figure, so our x2 is asymptotically stable, but x1 it's not asymptotically, but over time it is not going to zero, but x2 is going to zero. So we can say this is asymptotically stable. Yeah. So this is how we can find the solution of the system, which is defined in state space form, and how we can find the output equation or state equation. I hope this example is very useful for you. And also we have given the MATLAB code how to find the solution. How to write the code of the equation. And also we have discussed what is the concept of stability. Over time, we'll have come up with different terminology on stability. We'll explain on that particular example. So let's stop it here. And in the next lecture, we'll come up with some new topic on that is will be on if the system is coupled and how can we find in decoupled form using some concept that is called linear transformation concept. So we'll discuss that part in the next lecture. Thank you.